Hello grade 11, welcome again with you Mrs. Minna Raouf, your chemistry teacher. Today we will start our new chapter 21, Nuclear Chemistry, and section 1 talking about types of radiations. First, we will talk about the discovery of radioactivity. A French scientist named Henri Becquerel was studying a phosphorescent uranium compound in 1896. Becquerel discovered that uranium compounds spontaneously give off radiations. What meaning by radioactivity? Is a spontaneous emission of radiation by any unstable atomic nucleus. The nucleus. Before talking about the nucleus, let's talk about atom. You know the structure of atom consists of the nucleus and the electrons that moves around nucleus. And we have here inside the nucleus we have protons and neutrons. Protons with positive charge and neutrons with neutral charge. The atomic nuclei are made of proton and neutrons, which are collectively called nucleons. So, the protons and neutrons inside the nuclei called nucleons. In nuclear chemistry, an atom is referred to as a nuclide and is identified by the number of protons and neutrons in its nucleus. So, in nuclear chemistry, an atom is referred to as a nuclide and is identified by the number of protons and neutrons inside the nucleus. So, in nuclear chemistry, atoms will be nuclide and it identified by the number of protons and the neutrons inside the nucleus. A nuclear reaction is a reaction that affects the nucleus of an atom. So, the nuclear reaction is a reaction that affects the nucleus of atom. During the nuclear reaction, nucleus can lose or gain protons and neutrons. When the atomic number changes, the identity of the element change. So during the nuclear reaction, nucleus can lose or gain protons and neutrons. And when the atomic number changes, the identity of the element change. You can represent nuclear changes using equations, just as you do for chemical reactions. The reactant will be on the left and the product on the right, following an arrow. For example, the carbon has neutron isotopes with 3 different atomic masses: carbon 12, carbon 13, carbon 14. Carbon 12 and carbon 13 are stable isotopes, but carbon 14 is unstable and radioactive. So how we can differentiate between them? And also, we have 3 isotopes of hydrogen. Hydrogen 1, hydrogen 2, hydrogen 3. So we can identify the nuclides into 2 ways. The first way, by writing the symbol of the atom and write the mass number as superscript and the atomic number as subscript on the left side of the symbol, or write the element name and after that following by the atomic mass. This is the 2 ways that we can identify the nuclides in the nuclear chemistry. The radioactive decay. What's the meaning of decay? Decay is the release of radiation by a radioactive isotopes. So the decay is the release of radiation by the radioactive isotopes. And we have 3 types of radiation: alpha, beta, and gamma, emitted as unstable nuclei decay into stable nuclei. First type, alpha decay. Alpha consists of streams of alpha particles, and alpha particles are helium nuclei consisting of 2 protons and 2 neutrons. And we can represent the alpha particle as writing the symbol of helium, He, and the atomic mass and the atomic number as 4 and 2, or by writing the symbol of alpha. Decaying nucleus here lose 2 protons and 2 neutrons. So the atomic number decreases by 2 and the mass number decreases by 4. This is a nuclear reaction where decaying of alpha particle. The radioactive radium-226 decays undergo alpha decay, forming radon-222, and the alpha particle is emitted from a nucleus of radium-226. The radium here loses 2 protons and 2 neutrons. So this loss of protons will make the product radon, as shown in the nuclear reaction here. So the atomic number will decrease by 2 and the mass number decreases by 4. The second type of radiation, beta decay, from unstable atomic nuclei results in beta decay and produce beta radiation. And beta particle is high energy electron with -1 charge and is written as E is for electron and the mass number of electrons equals 0, and the atomic number will be here -1 or beta negative. So this is how we can write beta particles. The decay of beta particle causes the transmutation of the element. The decaying nucleus here turns into the nucleus of an element with atomic number that is 1 greater than the original one and same mass number. So during the decaying of beta particles, the atomic number is 1 greater than the original one and the mass number will be the same. Carbon-14 is an example of isotopes that decays by beta emission. An atom of carbon-14 here is converted into a nitrogen-14 because beta particles has only the mass of 1 electron and the mass number remains 14 because beta decay changes the neutrons to a proton. The atomic number here of the nucleus increases by 1 unit from 6 to 7. The third type, the gamma decay. Gamma ray is high energy form of electromagnetic radiation without mass or charge. Because of its high energy and penetrating ability, it can cause great harm to living cells. Gamma ray, written as a symbol of gamma, and this is a symbol of gamma ray, and during gamma decay only energy is released. So gamma decay doesn't affect mass number or atomic number. So during gamma decay only energy is released. And this is the differentiate of the penetrating abilities of the 3 types of radiation. That we have here different level of shielding. Alpha particle can be shielded with just a sheet of paper, but beta particles can be shielded by lead, wood or glass. Finally, gamma rays are the most penetrating and require shielding with thick layers of lead or concrete or both of them. The smoke detector. The smoke detector is a device that sounds alarm in the presence of smoke particles from burning object. So it contains a sensor that detects smoke particles that interrupt an electric current. It contains the unstable isotopes of americium-241, decays to neptunium-237 and helium, and this is 2 harmless isotopes by the following reaction. Americium will decay by alpha radiation and convert it to neptunium-273 and helium. Now let's show together how we can write and balancing nuclear equation. Potassium-40 can decay to calcium-40. Write the balancing equation for this reaction and determine the types of decay. You know that we have 3 types of radiation, alpha, beta and gamma. Alpha particles affect on the mass number and the atomic number, but beta affect only the atomic number, while gamma doesn't affect both of the mass number or the atomic number. So how we can determine and write the balancing nuclear equation? First, we will write the symbols of the two elements, potassium 40 and calcium 40. So here, potassium 40 with atomic number 19 and calcium 40 with atomic number 20. So what will happen here? This change it to this one. What's the difference? The mass number here is same, but the difference here in the atomic number. What's the type of radiation that affect only the atomic number? That's right, the beta radiation. And also it increases the atomic number by 1. So we will know that here the type of radiation will be beta. So potassium 40 19 will be calcium 40 20 and beta radiation. So beta decay has taken place in this reaction. This is how we can write or know the type of decay. Half-life. Half-life, or T-half, is the time required for half the atom of a radioactive nuclide to decay. So it's the time required of only half the atoms of a radioactive nuclide to decay. It's easy to measure and has been determined for many different isotopes. So half-lives are only fraction of a second, where others are billions of years. And this is the half-lives for some of the most commonly used radioisotopes, like hydrogen, carbon, potassium, and cobalt. The radioactive decay has provided scientists with a technique for determining the age of fossils and geological formations and human artifacts. By using the knowledge of the half-life of a given radioisotopes, one can estimate the age of an object in which isotopes is found. 4 different isotopes are commonly used for dating objects: carbon-14, uranium-238, rubidium-87, and potassium-40. Carbon-14 dating. All organisms take in carbon during their lifetime. Plants for carbon dioxide gas, and the animal from the plants and the animals that they eat. But the half-life of carbon-14 is about 5,730 years. Is short compared with the age of many fossils and geological formations. So carbon dating is used to determine the age of organism and object containing carbon. But rocks and minerals that are up to billions of years old can be dating by using radioisotopes with long half-life, such as potassium-40. The half-life equal 1.25 billion years. Uranium-238, the half-life is equal 4.5 billion years. And rubidium-87, the half-life equal 48 billion years. So we used the carbon dating for the organism and the objects that containing carbon, but the rocks and minerals that are up to billions of years old, dating by using the other isotopes like uranium, rubidium, and potassium. Now we have finished section 1. I hope you understood the session well, and see you in the next session. Bye bye.